Okay, welcome back. So this is the second part of the talk. So in the first part, we saw how to relate Floer homology in some sense to spectral geometry using this kind of estimates and like interpreted this as some kind of notion of bigness. Okay, so in the second part, the goal is to go from spectral geometry to hyperbolic geometry. And by putting things together, these two parts, one should be able to get some kind of relation between hyperbolic geometry and Floer homology. Okay, so well, before we start, let me just give a quick comment. So the relation involves this kind of weirder eigenvalue, right? So I don't know, lambda 1 is kind of very physically meaningful eigenvalue. It's like the pitch at which, if you think your manifold as a drum, this thing vibrates. This lambda 1 star is kind of more mysterious, right? So it will seem to be weird. Why would anybody study it? But it's actually, in recent years, it has become quite a popular object. So in particular, let me just add another remark. So lambda 1 star, so this first eigenvalue, plays a key role in a conjecture of Bergeron and Venkatesh. On the torsion homology of arithmetic hyperbolic 3 manifold. Okay, so in particular, well, what I studied, like if you have congruence covers, if you look at towers of coverings of these kind of objects, then their torsion grows much faster than you would expect. There's like exponentially large in the degree of the cover. And using this theorem called Chico-Newton theorem, which relates torsion homology to eigenvalues of the Laplacian, it turns out that really the key step to understanding this conjecture is to understand lambda 1 star. So and somehow it's nice that it plays a role also in this kind of more number theoretic, purely homological theorem. Okay, so it's a classical homology. Okay, so it's just to say that it's not some kind of number that nobody cares about except us, maybe. Okay, so yeah, so how to relate this to hyperbolic geometry? This theorem, well, if you look at the contrapositive, so for a hyperbolic 3 manifold, so if you have YG hyperbolic, then the Ricci, this you can check, this is minus twice the identity. So S tilde is -4. Okay, the three eigenvalues are -2, and S tilde is the sum of the two least, which is -2 plus -2. So you get this following corollary. So if you have a hyperbolic rational homology sphere, Y rational homology S3, and then if lambda 1 star, here it depends on the metric. Here I'll think about the hyperbolic metric. This is bigger than 2, then Y is an L space. Okay, so this is a spectral geometry way of proving that something is an L space. Okay, so yeah, I guess the natural question is like, this is a corollary, which is an assumption, lambda 1 star bigger than 2. And the question now is like how to verify, how to check if lambda 1 star bigger than 2. Okay, so the question of course, the basic thing one would like to know is like, is there any manifold that satisfies the hypothesis, for example? Okay, so yeah, so actually here is where the thing comes. So that there is a deep relation between spectral and hyperbolic geometry. Okay, and this comes it's slightly more general, but like we will focus maybe on hyperbolic geometry. And this is what is so-called the Selberg trace formula. Okay. So yeah, so before, so this is somehow in general, it's a kind of formula that gives you some relationship between spectral geometry, so eigenvalues of certain differential operators, and hyperbolic or other kind of symmetric geometry, so length of geodesics and volume and stuff like that. Okay, so yeah, so before writing down the actual formula that we will need to get some kind of understanding, let me just pause and go back to a kind of example, the simplest example of the Seberg-Trace formula, which should be familiar, I guess. So this is the basic incarnation of this kind of relationship between eigenvalues and geometry, is the famous Poisson summation formula. Okay, so what is this? Well, yeah, so if you have a function f in C infinity with compact support R, well, then the Poisson summation formula tells you that if you take the sum of the Fourier transform of the function, so this is the Fourier transform, at all integers, this is the same as the sum of the function itself at all integers. Okay, yeah, so these are very classic fact, and it's very useful in a lot of contexts. But yeah, so I guess the way it appears is that because this is, you know, you sum over two things which are the same, but they really have different meanings if you look at the way it comes up. Okay, so here really this is, you can think of this as a Seberg-Trace formula applied to y, which is S1, which is R mod 2 pi z. Okay, and the Laplacian here is minus dx squares over dx squared, so the second derivative, and this has eigenvalues 2 pi n squared. Okay, so the eigenfunctions are just the basic Fourier modes, right? So the e to the I n x. Okay, so really, you know, here you have two things appearing. So the sum over two things which look exactly the same, but it's actually very different. They have very different meanings. So these are the these appear the square roots of the eigenvalues of the Laplacian. Okay, and this, you can think of them as essentially the length of the geodesics on y. Okay, this is 2 pi, but up to that 2 pi, these are the length of the geodesic are just going around the circle, so that's n. So it's a length of geodesics. Okay, so, and this is very interesting because, you know, you have a sum, you know, one side only depends on eigenvalues, and the other side only depends purely on geometry. Okay, so the same thing holds, the similar thing holds in our context. So for us, okay, so you have your hyperbolic 3 manifold. Okay, so on one side, you know, you have this, on one side, you have all the data that comes from spectral geometry. So you get, you know, you have lambda 1 star, these eigenvalues here. And we'll just, you know, the natural quantity, as in the previous case, will be the square root of the eigenvalue. So let me define Tj to be the square root of lambda j star. Okay, and then on the geometric side, well, it's a hyperbolic 3 manifold, so you can think of its closed geodesics. So gamma closed geodesic. And a closed geodesic, well, on a, you know, it has once you're in a 3 manifold, you have two interesting quantities. So, you know, you have a loop, which is a closed geodesic, gamma. So you have the length of gamma. This is actually just how long the geodesic is. But you also have the holonomy. So the holonomy is like you pick a orthonormal frame, and you parallel transport it around. Okay, and when you go back, well, it's parallel transport. So when you go back, you get again an orthonormal frame, but it will be rotated, right? In general, this thing will twist around, and the angle at which you twist, it's called the holonomy of the geodesic. Okay, so this is it's okay. So this is an angle, and this is what is called the complex length of gamma. Okay. And yeah, so these are the two basic objects that will be useful for us. So yeah, let me just tell you how the formula looks like in this setup. So this is like a theorem. So pick so in the previous setup, so pick H, which is a C infinity function with compact support in R, which is even, let's say. Okay, and then and let's also assume, like for simplicity, y is a rational homology sphere. Otherwise, the formula is just slightly more complicated. But yeah, so the formula is the following. So again, you have the sum over H hat of Tj. So H hat is again the Fourier transform of H. So this is sum over all eigenvalues. So the sum over all eigenvalues. Okay, minus 1/2 H hat at 0. Actually, let me just put it on the other side. Plus volume of y divided by 2 pi h of 0 minus h double prime of 0, h double prime is the second derivative, plus the sum over gamma geodesic of L of gamma 0 cos of the holonomy of gamma. So holonomy of gamma, remember, is an angle, so you can take its cosine. 1 minus e to the complex length of gamma. Okay, so if you were worried about the fact that it's not really a well-defined thing, the complex length only comes as an exponential. So then the exponential is well-defined. 1 minus e to the minus complex length of gamma. And h evaluated at the length of gamma. Okay, so this is, of course, it's a much more complicated formula, but the basic structure is very similar to the Poisson summation formula. So on one side of the equality, everything you can compute it purely in terms of the eigenvalues. Okay, so this is what we call the spectral side. While on the other side, you know, it's a very complicated sum, but everything only depends on just on geometric data. So it only depends on the volume and the length of geodesics. So this is called the geometric side. Okay, so you know, you have this relationship, and this allows us somehow to, hopefully at least, to convert. You know, we want to understand stuff about the spectral geometry. So we want to understand stuff about the left-hand side, and in principle, we can access, you know, the right-hand side of stuff, which is much easier to compute. It's stuff related to length of geodesic and volumes, and there are softwares, for example, SnapPy, that can compute kind of stuff like that. So hopefully we can manage some kind of technique to use this relation to compute, at least give understanding, give bounds on eigenvalues of the Laplacian. Okay, so the very important thing is that this you can compute. Okay, so for example, SnapPy, which is a super cool software and to do computation hyperbolic geometry, outputs the volume of, if you give them 3 manifold, well, it gives you the volume and complex length of gamma for all geodesics with length of gamma less or equal than r. Okay, so if you say, oh, tell me all the geodesic for which the length is at most 5, then the SnapPy does it. Okay, And then you can somehow use this to cook up bounds for the Fourier transfer for the spectral side. So yeah, let me just tell you how one can use this how to just give you a basic idea on how this can be done. So how to use it. Okay, so let me just, the basic question is like, so the question is like, the question you should ask yourself is t squared an eigenvalue? Okay, yeah, so, the idea is that, here this relation holds for any kind of H, right? At least if as far as they're compactly supported and even. So the idea is that if we are able to plug in some specific H's that work well, then we can try to get some kind of information. Okay, so the way it works is that, because you can evaluate using, evaluate the right-hand side using SnapPy. So that gives you information about the left-hand side. Yeah, so how to, what's an easy way to say if t squared is not an eigenvalue? Yeah, so then the idea is the following. So pick H with the following properties. Okay, so we want, well, so we assume that we have all the geodesic up to length H, right? Sorry, up to length R. So, to compute, we need our H to be supported between -R and R. Otherwise, we don't know how to compute. So assume this as input. So to compute this, we need to know all the geodesic between -R and R. Okay, so we know. So let's say we know all the geodesic between -R and R. Then, well, to compute the right-hand side, we need to know. We need our H to be supported there. So pick H is supported in -R. Then, well, let's and we can also pick H such that the Fourier transform is positive for real parameters. And then H hat at the given t is this t here, is bigger or equal than 1. Okay, there's a lot of this function. They're not hard to come up with, okay? Okay. Oh, sorry. Yeah, so then, if t, so we this is a task to figure out if t is an eigenvalue. So if t squared is an eigenvalue, then, well, H hat, the sum of the H hat of Tj, well, this is bigger or equal than the sum, each, H hat is positive, it's not negative. And therefore, well, if t is an eigenvalue, this will be at least H hat of t, right? Which is bigger or equal than 1. Okay. But again, this we can compute. Wait, let me put it this way. This is bigger or equal than H hat of t, because, well, this is a sum if this is an eigenvalue, and this is bigger or equal than 1. Okay, and this, we can compute because we have this formula for it. Okay, so we can okay, yeah. So the idea now is that look at a very large collection of functions H that satisfy these properties, and try to get this sum as small as possible. And if you get it less than 1, for a given t, then you know that t squared is not an eigenvalue. Okay, so the way so the way to make this to make it more you know, the idea is that you can try to minimize. So to make it efficient, let's say, we follow this procedure, the work of Booker and Strombergson. Okay, and in particular, they were interested in this very similar problem, like understanding the eigenvalues of certain hyperbolic surfaces defined in a number theoretic way. Okay, so we really import their methods in our setup. And then, yeah, so what they do actually using these ideas is like what they cook up, they define, you know, using this method, you can actually, you know, the method I was talking about was for a single t, right? And then you can put everything together in a nice way. So what they build is like this function j, jy of t. Yeah, you can compute some kind of function, which is a function from 0 infinity to 0 infinity. And this is just a way to repackage in a nice way for each t what we were doing, such that if t squared is an eigenvalue, jy of t is bigger or equal than 1. Okay, so you can use this to show that stuff is not an eigenvalue. In particular, you can use it to prove that some manifolds they're not. Yes, well, sorry. Let me just give examples. Okay, we should go back to our original examples. Right? We had this Weeks manifold, which was this manifold, and the Meyerhof manifold, and they're very similar from the basic point of view of like volume and injectivity radius, but one is a null space and one is not. So actually, let's see what happens when you run this for them. Okay, so Weeks. You draw this function, okay, and well, I could show you the graph, but it's not particular important. So this is the cutoff 1, and JRT looks like this. So here you have 9, and JRT looks like something like this. Okay, so in particular, sorry, let me see JRT. This is 3. Okay, so you see that you know, if you had an eigenvalue less than 3, then this graph would have to be bigger than 1 there. So this implies that lambda 1 star is bigger than 9. In particular, it's bigger than 2, right? So this implies that this shows that Weeks is an L space. Okay, so well, this is well known. Like, if, for example, it's a branch double cover of a quasi-alternating knot, or like just from the surgery diagram I gave you, you can cook up a way to show that it's a null space. But I think the interesting thing is that the method here, it's a purely hyperbolic geometry method. We don't need to know anything about Weeks, except here the volume and the length of the geodesic up to 6 or 6.5. Okay, so it's a very purely hyperbolic geometry thing. So this tool is like a code that somehow you give them only things that if you are a hyperbolic geometry, you know, volume and length of geodesic, and this tool tells you, oh, this space is a null space. Okay, so yeah, I think another interesting thing is that, well, let's look at what happens for the Meyerhof manifold. Well, then. You know, you can run the similar thing. Yeah, and this graph looks really like this. Okay, so this will be, you have a 2 here. So here is square root of 2, and then here this is square root of 0.33. Okay, so yeah, so you see here that this, you know, this is about 1.4, right? So yeah, these two graphs looks extremely different. And here you see that even though they look, actually we can reverse the procedure here. So we know that actually, let me just say, yeah. So the basic things about the basic quantities, volume, ejectivity radius, didn't really say much about the Floer homology of Weeks, the difference in Floer homology. But here we really see, once you look at the spectral geometry, one has eigenvalue much bigger than 9, and here actually, this suggests that there is an it's a null space. It's not a null space, so there must be an eigenvalue less than 2. And here, the only place where it can be, it has to be above 1, right? So this implies that lambda 1 star of Meyerhof is about 0.33 or something. Okay, so this tells you that spectral geometry really sees the difference, while the basic quantities of hyperbolic geometry don't see the difference between Weeks and Meyerhof, at least quantitatively. Spectral geometry really sees that. So one has first eigenvalue bigger than 9, and it's a null space, and one has eigenvalue less than about 0.33. So and it's not a null space. Okay, so I guess, and in general, you can, if you look if you look at the paper, actually, there's a nice table in which you see really that there's some very we put the table of the first 100 manifolds in the Hawks and Weeks census. And there's a very nice, in blue we put the L space and in red not the L space, and you see a very nice correlation with the first, I guess, the some kind of where you expect the first eigenvalue to be. So in some sense, this should be a hint that this lambda 1 star is a very important quantity to study when thinking about L spaces, and hopefully also the L space conjecture. And I guess I'll stop here.